Hi, this is Tony Northrup for Train Signal, and in this video lesson I'm going to teach you about all sorts of secure protocols for the Sstp certification exam. If you love acronyms and memorization, this is going to be a blast. Okay, maybe this is one of the drier lessons in the series, but these types of facts are really easy to write questions about. So there's a good chance that the exam writers are going to be a little bit lazy, and this is the kind of thing that they like to test. Let's get started by discussing symmetric encryption. The first standard I'd like to talk about is DES, the Data Encryption Standard. This was the first official US encryption standard that they determined in 1979, and it held up for some time, but then we discovered that there were some flaws in the algorithm. Nowadays, we know it can be cracked in about a day. So that's not good, right? It has a 64-bit block size and a 64-bit key length, but only about 56 of those bits are actually used for the key because 8 bits are used for parity. 56 bits, that's a pretty short key, so that contributes to its kind of lack of security. Good old triple DES, 3DES. This is the DES algorithm run 3 times. It's really that simple. It still has the same 64-bit block size, but the key length is 168 bits. Now, remember when I said that the regular DES was 56 bits plus 8 bits of parity? Well, 56 times 3 is 168. That's how we arrived at that key length. Everything has to be encrypted 3 times using 3 different 56-bit keys, which makes triple DES 3 times slower than regular DES. However, the security grows exponentially. It's thousands of times more secure, and even today, it's considered quite safe to use. AES, the Advanced Encryption Standard. Now, AES is just the general term that the US government uses for their standard encryption algorithm. The name of the current AES standard is Rjndal. It's written there on the slide. I don't know. It sounds Icelandic or something. Of course, that's the name of the person who helped to develop it. The US decided that Rjndal was going to be the standard algorithm in 2002. This is the same algorithm that's used by the Wi-Fi encryption standard WPA2. WPA2 encryption is considered strong, as is everything that uses AES encryption. Here's a stream cipher that you should be familiar with, RC4, the Rivest cipher 4. As you might recall from another lesson, stream ciphers encrypt data 1 byte at a time, whereas DES and triple DES and AES take a block of data and spit it out encrypted. RC4 and other stream ciphers take 1 byte of data, 8 bits, encrypt it, and throw it out the other end. So they're really good for communications that are going across a wire where it's just a constant stream of little bits of data coming in and out. SSL and WEP encryption both use this. WEP is a Wi-Fi encryption standard that's older than WPA2. WEP is no longer considered secure though. RC4 itself isn't the best security, and in fact, depending on how it's implemented, it can be very weak, and that's the problem with WEP. WEP could have been more secure if they'd been more precise about how they used RC4, but regardless, RC4 just isn't the best. It was developed by Ron Rivest in 1987, and I don't mean any respect to him. He's a brilliant cryptographer, but cryptography has to withstand the test of time, and over time, some brilliant people managed to pick some holes in his algorithm. Back to the block ciphers, Blowfish was developed by Bruce Schneier, a pretty famous security guy, as an alternative to the original DES. One nice thing about Blowfish is it's public domain, so anybody can use Blowfish and you don't have to pay licensing fees to anybody. Like DES, it uses a 64-bit block size, but it has a variable key length. So you can plug in a key from anything from 1 bit. I don't know why you do a 1-bit key. There would only be 2 options, right? So it'd be pretty easy to hack into a 1-bit key. It's a 1 or a 0. You can go all the way up to 448 bits, which would be ridiculously strong. Blowfish holds up today. It's considered to be a very strong algorithm. Even though Blowfish is solid, they came out with a sequel called Twofish. Bruce Schneier worked with some others to develop this. It's a fast block cipher, so it works a little quicker, and it's considered very, very strong if implemented correctly. It uses a larger block size, processing 128 bits at a time, and the key length isn't quite as flexible as it was for Blowfish. You get to choose anywhere from 128 bits to 256 bits of key. 256 bits is considered to be very long, so just because Blowfish supports up to 448 bits, you don't necessarily need to consider it to be more secure. I mean, technically it might be, but they're both basically uncrackable using modern computing technology. Now let's go really old school and talk about the OTP, the one-time pads. A one-time pad is a shared secret. Again, this is symmetric cryptography, so both the encryptor and the decryptor need this shared secret. The thing about a one-time pad is the key is the same length as the message. While Twofish could have a 256-bit key, you could use that 256-bit key to encrypt a gigabyte of data. If you're using a one-time pad to encrypt a gigabyte of data, you'd have to transfer a gigabyte key as well. As you might remember from other lessons, the hardest part about using symmetric cryptography is getting the secret key between the person encrypting the data and the person who needs to decrypt it. Because, of course, if you had a way to send them secrets, you wouldn't need to be using encryption, right? So getting that shared secret can be really difficult. And if that shared secret is just as long as the original message, it becomes very, very difficult. So that's why one-time pads tend to be hard to implement. However, the great thing about one-time pads is they're uncrackable. I don't mean uncrackable with modern computing power. I mean always, forever uncrackable, theoretically uncrackable, because they're not vulnerable to brute force. All you're doing is you're taking a message, let's say it's 100 bytes long, and then you're adding it to a 100-byte shared secret. The secret's the same length as the message, so for every byte you just add them together. And then whoever receives the message, they just subtract out that key. If you happen to go past 255 in a byte, which is the maximum value a byte can represent, well, it just rolls back to 1. So you overlay the key over the message, add every byte individually together, and it could be anything. Depending on the key, it could be 100 bytes of anything. It could be your secret message, or it could be Shakespeare, or it could be the dialogue from your latest TV show. Whatever it is, there's no way for anybody to ever know unless they get that shared secret. Now this goes all the way back to the 1800s and it's been used by the military, and in fact it's still used today. And I'll tell you how it's used. If a government is sending a spy into a foreign country, well, they give them a huge one-time pad. This one-time pad could be in the form of a book. So a particular page of the book could be a one-time pad for some sort of message. The spy will know which book to look in, but nobody else will. Then you can send the spy a message and tell him in some secret way that the one-time pad for it is on page 137. He goes and he finds the book and he looks at that page and he uses the text of the page to decrypt the message. The message is uncrackable unless you figure out the system that they're using to retrieve the one-time pads. So here's a quick summary of the symmetric algorithms that I just covered. Good old DES, not very good at all, really. Uses a 64-bit key, but remember 8 bits of parity, so it's actually only a 56-bit key, and that's considered really short. It also has some vulnerabilities in the algorithm itself. It's a block cipher, and you should not use it. Triple DES has 3 56-bit keys, adding up to 168 bits. Just like DES, it's a block cipher, and it's good. It's not the best, but it's nice and solid, and you don't have to sweat it if you have it. AES is the generic term that the US government uses for their kind of official standard of encryption. And as you might expect, this is really, really safe. It has a variable key length, 128-bit, 192-bit, or 256 bits, and it's a block cipher, and it's great. You should use it. RC4 is a stream cipher, and it's outdated, and it's not great, and it has a variable key length, so don't use that. 3 more types of block ciphers. Blowfish, public domain, so anybody can use it without paying a fee, uses a 64-bit keys, and it's quite secure. Twofish, even more secure, uses longer keys, developed by the same guy along with a team. That's Schneier. And then the one-time pad, the key length needs to be at least as long as the message itself. It could be longer, in which case the person decrypting it just ignores any excess. Of course, it's a block cipher. And it's infinitely secure. It's completely uncrackable unless you get that secret key. So should you use it? Well, yeah, it's perfectly secure, but it's a pain to transfer that secret key, so it's not as usable as the others that have shorter key lengths. Now let's go over some asymmetric encryption algorithms. Good old Diffie-Hellman, of course that's named for the two fellas who worked this out. This is used for key exchange in asymmetric encryption, and it was really the first working example of asymmetric cryptography. With Diffie-Hellman, you generate yourself a public and a private key, then you send somebody the private key, then anybody can encrypt a message with your public key, and only you can decrypt it. So that way you can send somebody a password, which you could later use for symmetric encryption or anything else. Diffie-Hellman is key exchange. So look at that picture. Imagine that's Diffie on the left and it's Hellman on the right, and they're kind of exchanging a key between each other. The key length is variable. It's more of a general process that you can use for key exchange. RSA, there's that name again, Rivest, who was also responsible for the RC4 algorithm. Again, brilliant cryptographer. Shamer and Alderman worked up this algorithm that's now known as RSA, and it's still really commonly used. RSA includes procedures for key exchange, encryption, and digital signatures. The keys are much longer in asymmetric cryptography, so we have a variable key length from 1024 bits to 4096 bits. As I've said in other lessons, asymmetric cryptography is much slower than symmetric cryptography, which is why if you're encrypting large blocks of data, it's always done with symmetric cryptography. You generally only use asymmetric cryptography to authenticate things and then to transfer a shared secret for later use by a symmetric cryptography algorithm. RSA was developed in the late 70s. ECC, the elliptical curve cryptography. This general cryptographic procedure can use any key length. It's just this particular type of math that requires less processing time to generate public and private key pairs than does the RSA algorithm. That makes it good for mobile use. It's considered very strong. These public and private key pairs have the same mathematical relationship that they do in any sort of asymmetric cryptography. There are lots of different implementations of ECC, so the security and the details of it are going to vary according to the implementation. Now let's talk about hashing algorithms. I've covered the basic concepts of hashing in other lessons. Now I'd like to go into a little more detail about hashing collisions. Hashing collisions are a weakness of really any hashing algorithm. Let's look at an example. This is how hashing is supposed to work. You take your input, you put it into a cryptographic hash function, and it generates a message digest, which is a fixed length digest that uniquely identifies the original data without allowing you to return to the original data by using just the digest. So it's a one-way cryptographic function. Now let's look at a collision. You can see that I have shown two different inputs here, and they have a few differences highlighted in black. Well, the inputs are different, so if you run them through a hashing algorithm, they should generate unique digests, right? After all, a hash is intended to allow you to verify the integrity of a file, so if you make any changes to the file, it should always generate a new digest. Here's what happens. In this particular example, those two blocks of data will generate the same hash value. Now, of course, this is always theoretically possible with a hashing algorithm, because look how much longer this is than the hash. There'd be no way for every combination of data this long to make a unique hash, because there are simply fewer possible hashes than there are inputs. However, you should not be able to just change 6 bytes of data and get back to the same hash value. It should be very difficult and very rare for there to be collisions. Now I'll tell you a story. Back in, it must have been 95, I was one of the first developers for what is still a very large site with downloads on it. You've certainly seen it. It's the same one that's been around forever. We happen to get a very obvious domain name for that website. And I was working up a database that would organize the different files that would be available for download. Now, of course, I needed a way to uniquely identify each of the different files, as well as to verify the integrity of the files. So I used the Md5 hashing algorithm. Of course, Md5 is the sequel to the Md4 algorithm, and it was considered newer and better. Well, my application needed to process hundreds of thousands of files. And these are all really big files, creating these fairly small digests. And I left it running and running and running. And I came back on a Monday after it ran over the weekend, and I had a database error. See, I was using the digest as the unique key in the database to allow me to quickly look up records. And the key, of course, has to be unique. That's in the name. Anyway, two different files had generated the same Md5 hash. It was bound to happen at some point. Mathematically, it would have to happen. If I had an infinite number of files, there would be a collision somewhere. I had much less than an infinite number of files. I only had hundreds of thousands of files, but it did create a collision, and it meant that I could no longer use the Md5 to be a unique key. So I just want to make the point, collisions are a weakness of hashing algorithms. It is possible for two separate inputs to have the same digest. And for me, it happened in the real world, and it broke an app and required me to redesign the app. While Md4 and Md5 are hashing algorithms, SHA is a digital signature algorithm. So digital signatures, of course, generally have a hash built into them. You hash a file, and then you just encrypt the hash using your private key. The recipient of the file can calculate the hash of the file, generate a digest, decrypt your signature using your public key, and then make sure that the hash they generated is the same as the hash that you signed. This verifies the integrity of the file and verifies you as the owner. So just like most of these algorithms, SHA has been through a few different generations. SHA-1 had lots of collisions in it, and that was a problem. SHA-2 is the algorithm that's currently in use. And they're working up a new SHA-3. There's this kind of process where people select different elements of it and verify that everything's working out well. So before it ever goes official, it has to go through this selection process. You can see at the upper right of the slide that there are different variations of SHA that use different block sizes and hash lengths. Now, I mentioned Md5 earlier. That was the algorithm that I picked, and it was pretty fresh and new at the time and considered pretty great. 1991 seems like a long time ago now, though. Uses a 512-bit block and generates a 128-bit hash. Nowadays, there's also a newer choice, which is Md6, and it does have some improvements. And of course, as I explained earlier, collisions are possible. Md5 still seems to be the most common hashing algorithm. Another family of hashing algorithms is RIPE-MD, which is based on the Md4 and Md5 algorithms. This stands for Race Integrity Primitives Evaluation MD. That really rolls off the tongue, doesn't it? I think that's worse than Rigendale. RIPE-MD has a variable block size, and it generates either a 160-bit or a 128-bit hash length. However, the 128-bit version isn't considered secure at all. It has a lot of collisions, so you really need to use the RIPE-MD 160 based on the more recent Md5, and it's more secure. Now we'll talk about HMAC, the hash-based message authentication code. HMAC is used for data integrity and authentication. It's just like a regular hashing algorithm, except they cram in an extra secret key. In fact, it uses either Md5 or SHA. You can kind of swap out the hashing algorithm as you want. If you use SHA, the 256 variety, you can call this HMAC-SHA-256. So that's how they uniquely identify the algorithm plus the hashing function that you chose. The strength of HMAC depends on which algorithm you choose and the length that you plugged into the hashing algorithm. What you're doing is you're using a regular hashing algorithm and then putting in a secret key. The secret key makes it more secure than just a regular hashing function, though. So now let's round up the different hashing and digital signature algorithms that I talked about. SHA-1, of course, not good, 168-bit hashes, and it's considered very insecure. SHA-2 is much better. It generates a hash of 256 bits or higher. and it performs 64 or 80 rounds of calculations. Md5 is kind of the hashing algorithm of choice right now. Does have collisions, but that's kind of unavoidable. It generates a 128-bit hash using only 4 rounds of calculations. RipeMD is based on MD4, and MD4 is no good. Therefore, RipeMD is no good. RipeMD 160 is based on MD5, and MD5 is better than MD4, so RipeMD 160 is better than just regular RipeMD. Hmac just adds a secret key to your hashing algorithm, so the hash length and how many rounds it does is based on the underlying algorithm, and it is considered very secure. It improves upon the security of either SHA or MD5 by adding that secret key. Now let's talk a little bit about different ways to encrypt communications as they're crossing a network. Up first, what I think is probably the most commonly used, which is SSL and TLS and HTTPS. HTTPS actually uses TLS, and TLS is based on SSL. It supersedes it. It's an SSL certificate that you'll put on your web server. But then HTTPS itself is using TLS, leveraging that SSL certificate. If you can kind of see how those three terms interrelate. Anyway, all the different protocols and algorithms are kind of working together to authenticate the server and encrypt the communication. TLS itself also has the capability to authenticate both the server and the client, and you will see that used occasionally, though it requires the client to have a certificate that the server can authenticate in some way or another. The nice thing about these algorithms is they don't require the client and the server to have a shared secret. They use sort of a Diffie-Hellman exchange to establish a shared secret using asymmetric encryption. Then symmetric encryption takes over for performance reasons, encrypting all the data that's going back and forth with a shared secret. SSH is secure shell. It's basically like a VPN that you set up directly from a client to a server that you're managing or transferring files to and from. It's really common in the Unix world. It supports both encryption and authentication, and you can channel any sort of network communications through a secure shell. I just want you to be familiar with the term. Now let's talk about IPsec, which is just short for IP security. IPsec has two standards, and that's AH, Authentication Header, and ESP, which we'll talk about in the next slide. And nobody really uses AH, but you will see it on the tests. It's the kind of thing they test on, so I do want to cover it. All AH does is add an authentication header to a packet. So you can use this to verify that the packet hasn't been changed and to digitally sign packets so that you know that they're originating from a trusted source. AH just creates a hash of the packet plus the shared secret key between the client and the server, probably established using asymmetric encryption. So the recipient verifies the hash and makes sure that the message hasn't been modified. That's all it really does. Doesn't provide any encryption. ESP is basically everything AH is plus encryption, and there's no reason not to use ESP, which is why I say nobody really uses AH. ESP does the same stuff. Besides just adding in the authentication header, it encrypts the contents of the packet. So remember this, AH is authentication and data integrity. ESP is authentication, data integrity, plus that all-important encryption. I also want to mention Sstp. Sstp is really just a VPN protocol, but nowadays it's being used for just about everything because Sstp has one unique feature. It uses HTTPS as the underlying transport. And HTTPS probably sounds familiar because I talk about it all the time. This is the way clients authenticate web servers and then encrypt communications going to and from the web server. And it's really common. Every time you go to a banking website, they got to use HTTPS, and you know what that means? That means firewalls have to allow HTTPS through them. So Sstp kind of cheats. It uses this protocol that's designed for authenticating websites, but it uses it as a VPN, so it can transfer any type of traffic, encrypted, authenticated, securely across the network to a different destination. That's what a VPN does. Because it uses HTTPS, it means it will work through just about any firewall and proxy. The firewalls and proxies that you have at hotel rooms and in people's homes. So if you set up your employees with an Sstp-based VPN, they can use it from just about anywhere. If you're developing a custom app and you need to encrypt communications, we'll just use SSTP. Doesn't matter what the underlying protocols are, it's going to be tunneled through HTTPS and it will work in just about any network. The downside to SSTP is that it bypasses all network level security. Firewalls and networking equipment can't look inside the encrypted packets. They could decide to drop it, but they can't examine the contents of the packet and make application level decisions about whether to filter it or allow it through. So you basically bypass your firewall security and any network level security that you have. You have to rely entirely on client and server security. Another protocol I want to discuss is SMIME, Secure MIME. MIME is basically the format of email messages being transferred on the internet, and SMIME adds digital signatures and encryption. Now, of course, encryption provides privacy, and digital signatures protect the integrity of the message as well as authenticating the sender. SMIME uses asymmetric cryptography, which means everybody needs certificates. And for that reason, it doesn't work well on the internet because you personally don't have an internet certificate. Well, some people do actually, but there's no commonly accepted standard. While many different email clients support SMIME, nobody seems to be using it in any way that works universally. So SMIME is really common for intranet email. When you're sending messages to Bob, they'll be encrypted and authenticated, and that works out great. If you're sending messages to me, well, we don't share a PKI. We don't share a server. Therefore, if you send me an encrypted message, I won't be able to get to it. This is Tony Northrup for Train Signal, and thanks so much for watching this video lesson.